Welcome to the LemnaTec Academy. In this video, we will explore how to analyze hyperspectral data in LemnaGrid. This video assumes that you have watched the videos in class 3. Let's switch to LemnaGrid. Back in LemnaGrid, we start with a basic grid with just one disk reader. However, we can't use it for hyperspectral data. Hyperspectral data need a special reader device called disk hypercube slicer. So let's replace it and open it. If you open the hypercube slicer for the first time, you get an error message claiming that the input path is not set. Of course it is not. We didn't have the chance to do it yet. So let's select the file. We identify hyperspectral data cubes by the header file of the main data cube. If you export a snapshot from Lambda experiment, each hyperspectral data set is found inside a subfolder. This folder contains multiple files: 3 hypercubes, the actual data cube, the white reference cube, and the dark reference cube. Optionally, a white CSV file, and some more files which are not relevant, like the JSON files, some PNGs, and thumbnails. Each hypercube consists of 2 files, the header file and the data file. The header file has the extension HDR. The data file has no extension, or something like EMG. If this is an exported snapshot, then the files in this folder have predefined names. The main data file is called data and data HDR. We need to select the data file as the raw input data. There's an Infer other file names checkbox which is pre-checked. This means that all other file names are inferred from the name of the data file using the LemnaTec standard for naming these files. There are 2 more checkboxes. Normalize. We can work with raw data from the data cube itself, or we can normalize the data using the white and dark reference data cubes. The latter is recommended and hence pre-selected. If the optional white CSV file is available, then you can select the white reference calibration box and enter the file name there. If available, it complements the normalization. The white reference target might not have the same reflectance at all wavelengths. This is documented in this file. This information can then be used to improve the normalization of the hyperspectral data. In the example data, we do not have a white CSV file, so we leave it unchecked. With the data file selected and all relevant checkboxes selected, we can load this file by pressing the Apply Changes button. We see a first false color preview of our hyperspectral data. Hyperspectral data are usually too big to be passed through the grid. Therefore, a lot of the analysis is done already here. We have a couple of options in the Mode section. Preview. This creates a false color preview based on the information in the header file. Slice by. A normal grayscale image is a 2-dimensional array of values, and an RGB image can be seen as such as well, although one may argue the color channels are a 3rd dimension. However, a hyperspectral data cube is really a 3-dimensional object. It has 2 spatial dimensions and 1 wavelength dimension. In order to display this in a 2D fashion, as here, we could take a slice from this cube by cutting through the cube while keeping 1 spatial dimension or the wavelength constants. Line refers here to the axis of movement of the hyperspectral camera. So we get an image with all wavelengths as if the scanner has stopped at one position and took the image there. The other dimension is then the wavelengths. Sample refers to the position of one pixel on the camera sensor, hence the other spatial dimension. Band refers to the wavelengths. The next mode we can use is gray. This creates a grayscale image from the hypercube using a Gaussian profile with a peak at peak and the width determined by minimum and maximum. Color takes selected wavelengths and creates a false color image. This is similar to the preview, but you can select the wavelengths for each color. Wavelengths returns an image that is interpolated between the two bands closest to the given wavelength. The values at minimum and maximum are not used. Vegetation index. This is probably the most used mode. Here you can select a vegetation index from a huge list of predefined indices. See the list at the description. For instance, we can use the NDVI. Please note, if we work with normalized data, and we should do that, all outputs results are multiplied by 256. This guarantees that we have not black-only images. Remember, LemnaGrid expects all images to have values between 0 equal to the darkest and 255 equal to the brightest value of the pixel. We have a few more options in the Advanced tab, but I didn't talk about it yet. I will come to this in a moment. For now, let us stick with the NDVI. We can now continue with the grayscale segmentation techniques we have learned before. We use a threshold device to do the segmentation. The predefined threshold works already well. We have multiple wells, so we need a vessel configuration link. We have one row with 6 columns. Doing one row with 6 columns is a bit tricky, so I use some tricks. We need to convert the binary image from the threshold into an object list. Now we have to merge the objects within one position. We need to add the well name to the objects. Now I add a color property to add the values from the NDVI to the objects. We have to send the NDVI to this device. I use a loop through for this. Remember, I said that the values are multiplied by 256. In order to get real NDVI values, we have to correct this. We use a grayscale calculator for this. This error message appears only if you have reduced the number of inputs to 1, so we can ignore it. If we check the tooltip, we have now reasonable numbers in the image. And finally, we need to add a writer. But remember, we need here an RGB image, and therefore we need to convert our grayscale NDVI image to a pseudo RGB image using the universal converter. If we check the tooltip, we see reasonable gray values representing the NDVI for each object. We can do the same with all the outputs I have demonstrated from the Hypercube slicer. You may need to add multiple Hypercube slicers, but that's not an issue. We shall not forget to add names to the reader and the vessel configuration maker. But what if we want to use an index that is not listed in the Hypercube slicer? Then we have to calculate it by our own, and the Hypercube slicer has to provide the individual gray images for each wavelength. Here we can take advantage of the Advanced tab of the Hypercube slicer. Let me demonstrate it. I will use a second Hypercube slicer to do so. We switch to the Advanced tab and load the Hypercube. At the bottom, we have now two other options. First, we can select slices. These are slices along the same dimensions we have used in the simple case. However, we can now create multiple slices. But more importantly, we can select multiple wavelengths and get one output port for each of them. Let's assume the modified red edge normalized difference vegetation index is not part of the list of indices directly supported by the Hypercube slicer. Then we would need the following wavelengths: 445 nanometer, 705, and 750. We enter them one by one here and press Enter. The image we see now represents only one of these wavelengths. Our Hypercube slicer has now three outputs, one for each wavelength. We can now use the grayscale calculator to calculate the index. We need three inputs and connect them. The first is for the 445 nanometer and the last for the 750 nanometer wavelengths. As I said, A stands for the 445 nanometer wavelengths, B for the 705 nanometer, and C for the 750 nanometer wavelengths, because we input them in this order into the grayscale calculator. So our formula shall be C minus B divided by C plus B minus 2 times A. As expected, the image is basically black, but we have meaningful values here. Let's add some scaling factor so we can see the result better. Let's try 128. The image is now a bit brighter and we can see the structure. Images like these can even have negative values. Let's remove the scaling factor so our output has the real data, not the scaled one. We could send this data through the same pipeline as the NDVI above. However, the segmentation would be a bit more difficult as with the NDVI. The border of the plants looks somewhat blurry with this index. Since we have used the same hypercube twice, we can use the segmentation done using the NDVI and add only a writer and a color property device with the values from this calculation. I use an amplifier device to amplify the data from our calculation, so we can use it as an input image for the result image created by the writer. You may remember that the writer takes only RGB images as input, but our result is a grayscale image. Therefore, we have to convert it using the universal converter. So that's it. You have learned today to analyze hyperspectral data using LemnaGrid. LemnaGrid offers already a wide variety of indices, but with the grayscale calculator, you can create even more. See you in another video of the software and analysis training.